So U is our universal set, you know. U. And A and B are subsets of the universal set. This is subset, right? Here's what I want you to prove. This I will prove. One of De Morgan's laws, that A union B complement, C is complement, correct? You remember that. For instance, A complement is what's in U but not in A. In U but not in A. That this is equal to A complement intersection B complement. And, oh, good, the young man, he left. Come in, we're doing a TV presentation. Now, if you have any imagination, and I hope you do, you'll see this formula is like a formula we had in logic. You remember the logic formula? Does it remind you of this formula, a proposition P or Q, and the complement, that's the negation in logic, we saw was equal to or equivalent to the negation of P and negation of Q. Notice the similarity. Hello. Super. Oh, are you taking? Where can I put? Ooh, wait. Yeah, let me place you somewhere safe. I don't know. How about in the back? Yeah, in the back, away from each other. So you guys can work till 12:30. Yeah, separate from each other. Don't sit in each other's lap, please. Okay, we're going to have a problem on the quiz like this. How do you prove a set A, or the left side, is equal to the right side? Yeah, move away. He's a little, go all the way. Beautiful. So, the way we prove two sets are equal, we show this. The left side is a subset of the right side and vice versa, which means right side is a subset of the left side. Like in algebra, when you show two numbers are equal, A is equal to B, if A is less than or equal to B and B is less than or equal to A. Okay, so here is the proof. And first we're going to go one way. We start in the left side, take an element and show it's in the right side. And then step 2 is the other way. And the quiz at 11:40 will be like that, okay? Easy, open book. Okay, so here it is. Let X be in the left side. This means X is a member of the left side. A union B complement. Correct? So if you're not in a set, you see this is the complement of A. So it means you're not in A union B, correct? Look, draw a picture, Venn diagrams. You have a set U, and you have a set here E. Then this is U minus E, and that is the complement. That's the complement, this part, correct? So if you're in the complement, it means you're not in E, right? Or it means here, then X is not. You write not like this. You put a number, very suggestive. Students, the funny thing about students, they don't guess. Why would you do this? You're inventing notation. How would you write if this is X is in E? How would you write X is not in E? I mean, isn't this Wouldn't that dawn on you as a good way to do it? Okay, so it's not an A union B. Now, you know the union of two sets, something is in the union, A union B, if and only if it's in A or B. So if it's not in the union, it's in neither. It's in neither. Or X is not in A and X is not in B. Correct? Now, if X is not in A, it's in the complement. Correct? If this is your universe, every element is either in the set or in the complement, right? So if you're not in the set, therefore, I'm running out of words, or hence, therefore, X is in the complement, and, again, and, X is in B complement. Now, if it's in both of these sets, it's in the intersection, right? The intersection of two sets is this, correct? That's the, if this is one set, that's another, this is the intersection. Or, X is in the intersection. And you write intersection this way, B, C. Now look, we started with an arbitrary element here, and we have shown that it's here. So every element in the left side is in the right side. Hence, another therefore type word, hence, this first set, A union B, complement, every element there is here, or this is a subset of A, C intersect B, C. Correct? First half of the fight. This is so easy. Now we go the other way. If you're in the right side, you're in the left side. Okay? So, that's it. Let's go up to 2. Oh my. I have a collection of worthless pens. Let's find one that works. This one doesn't look brown. Is this good? That's red. I don't want red. How about this one? What's the probability it's good? It's good. Okay, so number 2. Start with an arbitrary element in the right side. So, let X be in the right side. AC intersect BC. So, if you're in the intersection, you're in both. This is so easy. So X is in AC, and, correct, X is in BC. Beautiful. Okay, you're here, you're there. So, therefore, if you're in the complement, you're not in the set, right? If you're in the complement, you're not in the set. And X is not in B. So you're in neither of the sets. You're not in A, you're not in B. Hence, you're not in the union. Correct? You have two sets. You have a point that's in neither, then it's not in the union. If it's not in the union, it's in the complement. Or X is in the complement of this. So what did we do? We started out here, we're there, and we ended up being here. Hence, one more hence if you like, every element here, AC intersect BC, is also in this set. That means it's a subset, so you write it as A union B, C. So I have 2 subset relationships. Beautiful. So what do I have? I've got this one we've proved, and we proved this one here, the bottom, correct? And I'm playing to the camera. Okay, so that's like A is less than or equal to B, B is less than or equal, then they're equal, right? When are two sets equal? If each is a subset of the other. So this relation, this red one, and this double check implies they're equal. Therefore, because of check and double check, we have it, that this equals this. A union B given C is AC intersect BC. Okay, any question? Okay, I'm doing all this stuff. I used to evaluate the assistants at the University of Michigan. And one of the things is the board work. My board work, I give myself a C, I'm sloppy. You know, board work should be like this, you know. But I get an A in contact with students. You know, you look the student in the, do you understand it? Do you have a problem? You know, not, the bad teaching is like this. You understand? No, you got it. You know, do a little business. Okay, so you folks will have a quiz at 11:40, something like this. Beautiful, wonderful.
Only one problem.
One problem, and then we're done to the final. Does anyone know when our final is?
Thursday,
Yeah, no, that's generic, but you know the exact date? See, this is a world record. Are they making the statement heard? Is the administration listening? I've taught at 12 schools. I've never been at a school where days before the start of the final, you don't know when your individual finals are. Usually in most schools, you know from day one, from the first day of class, when the final will be. Some places even earlier. For instance, University of Michigan, University of Tennessee, wherever you're thinking, when teaching will start in the fall of next year. The fall. That's all on the website. Are we listening? Can we kind of, you know, take care of that problem? Okay, everyone wrote this down, and so you're ready to go in 20 minutes, right? You're ready to do one like that. Don't look, there's consternation. Here's a new word, I'm teaching English. Consternation. That's being uptight. Consternation. Okay, I'm erasing, folks. Now, we're working on the probability chapter, and that's it. After today, we have 2 weeks, correct? Because we don't meet Thursday. And so next week and the week after, so we have 4 more sessions. Hopefully, we'll know when the final is. Okay, you got it? You got it. Okay, so let's go back now to our probability a little bit. This was set theory. Now we're going on to good old, that's chapter 5. We're done with 5. We're doing counting and probability, chapter 6. No good. When something is bad, remove it from the bin. This looks okay. Chapter 6. Counting and probability. Okay, guys, this is being recorded, so they're going to hear your voice. Maybe somebody from administration will come and, you know, work you over. Okay, counting, we did a lot of this already. Let's get on with the show. you have a makeup of that, and now a calculator. What do you need a calculator for? He's doing a problem. Yeah, you don't need a calculator for that. Is this the number? He's doing a problem. Write it as the product of primes. Try and see, can you divide it by 2? No. Then try 3, then try 5, that's all. I mean, I think everyone after the 5th grade can divide numbers and see if it goes in. They can do long division, 4389. See? Another message, without calculator you can't do this. Okay, you can do it. Okay. Here we're on with our show. Let's see what we got here. Good. Okay. We were looking at equally likely probability. That's the first thing we did. Equally likely. Likely probability. Okay, so I want to step back. Probability, we were looking at finite probability. You do an experiment, you throw a coin, it either comes up one side or the other. You have a die, you know, a cube with 6 faces to it. You have a cube, right? And equally likely that you'll get heads or tails. Equally likely when you throw a die that you'll get 1, 2, 3, 4, 5, 6, right? You throw 2 die, a red one and a black one. Then you have 36 possibilities, right? I can be 1, 2, 3 up to 6, and J can be 1, 2, 3 up to 6. So 6 times 6, 36. Those are equally likely. So this is your sample space, right? We looked at all those examples. As 2 elements, or 6 elements, or 36, equally likely, and this is an event, a subset of that. That's, E is called an event. Something happens. For instance, I throw a die, and the numbers are 1, 2, 3, 4, 5, 6. I say, what's the probability of even? So that's 2, 4, 6, 3 over 6. So we define the probability in the equally likely case, the number of elements in E. This symbol, hashtag, the number of elements in E over number of elements in S. Right. So we did that, got it. Okay? So let's look at a couple more homework problems. Let's look at number 6. I don't want to look in the book what's the number, but here is the problem. I'll say it in words. I throw 2 dice. It's an irregular word. 1 die, 2 dice. You see, it's not dice, dice, die. Okay, so I throw 2. And so the sample space has 36 elements. So if I take a sample space with 36 elements, one cube could have an I and the other could have a J, right? And I could be 1, 2, 3, 4, 5, 6, and J could be 1, 2, 3, 4, 5, 6. So I and J both picked from the set 1, 2, 3, 4, 5, 6. Correct? That's that guy. That's the experiment of throwing 2 dice. And so the problem is, what's the probability that the sum of I and J, when you throw it, is less than or equal to 6? So the event we're looking at is the set of IJs here such that I plus j is less than or equal to 6. See, and the question is, how do you get the probability? Okay? Well, how can you get less than or equal to 6? You could get 2, a 1 and a 1, right? You could get 3, 2, 1, 1, 2, yeah? You could get 3, 4, 5, 6. How can you get less than or equal to 6? It's this. 2, 3, 4, 5, 6. Beautiful. Is that the sum less than or equal to 6? It could be 2, 3, 4, 5, 6. So, this number that I'm looking for is what's the probability of this, plus the probability of that, plus the probability of that. It's the sum of 5 probabilities. Okay, so for instance, that ij, such that I plus j is 2. That's one possibility, right? Or that it's 3. The probability of those pairs, I and j, so that I plus j is 3, and 4 and 5 and 6. Got it? I think everyone understands. This is 2, this is 3, then you would have 4, 5, 6. So there are 3 more terms, right? 3 more terms. What is the probability of this first one? How many ways can I get I plus j to be 2? Only if both are 1, right? 1 and 1. So that's one possibility over 36, right? Using this definition. Okie doke. That's that. Now, how can you get a 3? Well, for a 3, you could have a 1, 2, or a 2, 1. Correct? I, 1, j, 2, or vice versa. So there are 2 possibilities. How can you get 4? How can you get 4? Well, you know, 1, 3, 3, 1, and 2, 2. 3 over 36. How can you get a sum of 4? 1, 3, 2, 2, yeah, 3, 1. So that's this one, that's this, the next one, this is 4 over 36. How many terms are there? 1, 2, 3, 4, 5, 1, 2, 3, 4. I've done it real quick for you, this. These numbers, right? Okay, just the last one. I see a confused look. When you see a confused look, how can you get 6? You see, the first could be 1, 2, 3, 4, or 5, right? 5 of them. That's why I have 5. So it could be, how do I get 6? It's this, 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 that. That's why I have a 5, right? Pretty easy. Okay, so you add up these probabilities. What do you have? I have a 5 and a 5 is 10. One more. 15 over 36. Cancel a 3. It's 5/12 is your final answer. Is that easy? Yeah, piece of cake. Okay, what's problem 14? Let's do 14. This was a certain problem number 8. Let's do 14 here. Beautiful. Look. Where am I? 3A, number 14. Okay, let's look at the exercises 6-1. 14. Number, what was this? 6-1. Let's look at 6-2. Let's look at 6-2. Yeah, and I didn't put the page, so I don't know what the next problem is. Okay, minus points at this point for me. Beautiful. Now, let's see where this could be. Number 8. Number 14. Beautiful. Number 14. And this was. Okay, how about number 14 on 304? Let's do that. 3 people have been exposed to a certain illness. You know what exposed is? Ebola. Someone breathes on you. Ha! Spits on you, God forbid. 3 people have been exposed to a certain illness. Once exposed, a person has a 50-50 chance of becoming ill. Sometimes your immune system is good. You don't get the illness. 50-50. Three people. Okay? And these are independent events. That is him getting sick, me getting sick, somebody else, the 3 people, they're independent. Okay? So 3 people are exposed to a certain illness. Once exposed, person has a 50-50 chance of becoming ill. What's the probability that exactly one of the people becomes ill? Got it? You got 3 people, okay? And one of them becomes ill. Oh my goodness. How is that? Let's look at that. 3 people. Let's look at it intuitively. 3 people exposed. Once you're exposed, you have a 50-50 chance of getting the disease. Okay? What is the probability that exactly one, not 2, not 0, exactly 1 person becomes ill? What could happen? Let's step back from the problem. You have 3 people, right? So 0 can get sick, right? 0 people could get sick. Correct, that's possible. Exactly 1, our question, or 2, or everybody could get sick, right? Now, what do you think the probability nobody gets sick is? Well, what is your sample space? How are we going to, look at this? Well, you have 3 people, so look at triples. What's a triple? 3 people, correct? So this is person P. Well, let's see, person 1, person 2, person 3. There are 3 people. Correct? Now, how can this work? Well, each of these could be get sick or not sick. How should we write sick? S for sick, not sick, I suppose like that, complement, healthy, yeah. Okay, so how can I have, what's the sample space? All these are equally likely. what could happen? So you have two possibilities for this, sick or not sick. Sick or not sick, sick or not sick. So what are the possible outcomes of this experiment? You take the three people, you expose them, what could happen? Well, you could have 0 people getting sick. So that means that would be something like this, right? None of them get sick, correct? Well, how about one person getting sick? Well, it could be this guy, or this guy, yeah? So, what would that be, getting sick? It would be a sick here, or a sick here, yes? And the other two, not sick. Okay, that means SC, 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 correct? Now, what about, so that is exactly, this is 0 people getting sick. These are 1 person getting sick, correct? Okay, how about 2 people getting sick? Well, I'll continue the drawing. We need a little more room for the triples. Let's continue them here. So the triples, you've got person 1, person 2, person 3, right? So this is 1 person gets sick. Sick is S. Now, 2 people get sick. 2 could get sick. If 2 get sick, then 1 is not sick, right? Well, who could be that person? This guy could be non-sick. The second person could be non-sick. The third person. And the other 2 get sick. These are 2 sick people. Bing, 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 bing. Okay? So these are the situations where 2 people are sick. Now, the worst case, everyone gets sick. That can happen only one way. That's SSS. Now, notice what this adds up to. How many different cases are there? 1, 2, 3, 4, 5, 6, 7, 8. 8 cases. 8 cases, meaning 8 triples of the letters S and not S, not sick, right? 8, okay? There it is. These are all equally likely, 8 outcomes, okay? So what is the beautiful that 1 person gets sick? What is the probability that exactly 1 person becomes sick? Okay, well, where is that? 1 person becomes sick. Here it is. How many are there? 1, 2, 3 of such cases. Correct? Altogether, the sample space S has 8 elements, right? Now, this event, let's call it E1, exactly 1 person sick. Gets sick. That's this. 1 sick, there are 3 of them. So the number of elements in E1 is 3. So the end becomes 1 person, what is probability that it becomes exactly 1 person becomes ill is the probability of 1 person being sick is 3 over 8. Number over E1 over total number of cases, that's S is 3/8. Got it? Okay. Now, what's the next one? The 2 people get sick. What is E2 is people in that set? Number of elements in E2. Where are they? Two S's. That's these cases. Double S, double S, double S. These are two people get sick. Okay? So how many are there? Three. Right? So this is also 3. So P of E2, two people get sick. Number of elements in E2 over number of elements in S is again 3A. Okay, what about a last one? What about the last one? None of the people get sick. The best case, nobody's sick. Let's call that event E. No one gets sick. So that's all the complements. That's this one. That only happens one way. Nobody gets sick. So the probability of that is number of elements in E over number of elements in